Thanks a lot for inviting me. And Eleni, feel free to interrupt when I'm going over time, or when there's 5 minutes left, you can raise your banner like in
I will
real
let you know.
conferences. Okay. And people can shuffle their chairs, but I won't hear them. Okay. So, right. So thanks. So this is actually, this is an opportunity for a talk which I never managed to give because the paper was accepted at Stacks, and I couldn't go to Stacks because of the COVID hitting, and we had to cancel our trains. So, so this is a brief introduction on that. All right, so basically this is based on, like I said, on a couple of papers. One was a brief announcement in PODC 2019, and the other was this on Stack's paper on termination of flooding. So this is not a classic temporal graph theory, but there's some connection at the end, which I hope to make us more in the realms of distributed algorithms, but there's some similarities. Okay, sorry, I'm trying to change my view here so that I can see my slides better. Okay, I give that up. All right, so a few of you probably seen this talk a little bit before, including Eleni, I suppose. All right, so the motivation, let's say, for us is we have this group of WhatsAppers, this new breed, maybe amongst us also, who would just forward any message you receive to everybody else in your group, and you basically just send so many messages, especially nowadays in the lockdown. People have become more and more WhatsAppers. Hopefully now it's coming down, I suppose. So I'm calling this breed of people as WhatsApper, those who just, because that's the platform I'm getting them on, social media. So often these people have a great interest in politics, and they, end up sending fake news. So I'm calling them the amnesiac, ambitious WhatsAppers. So why these words? Because I believe they're very discerning people at least in their mind. So they don't really send to everybody. They don't send to the persons who just send them the message. So they're careful in that. But the problem is, if you send so many messages, you're likely to become forgetful. You're just likely to keep sending the same message if it comes back to you again. Nobody's really reading them so carefully. So so these persons are forgetful. So that's the amnesiac part. But they will just keep flooding the message again and again. And the real important problem is that, will such a message ever stop? I'm sure many of you suffered at the hands of such people. So you'll be interested in the question, right? So the nice thing is we can reduce it, as we always do, to graphs, right? So we can reduce it to a trade of computer science, that is reducing everything to graphs. So we can reduce this the problem to a graph, and we all know what a graph is, but just to emphasize, the graph GVE is a formal model for the network. So the network is where this is being sent, and where vertices are the nodes and the edges are the connections, right? So now this is a formal model of the network, and to emphasize again from the distributed community part, but for I think for regular graph theory, temporal graph theory, it's just the same. It seems to be exactly the same way as you discuss processes, I suppose. And in the distributed community, it's a little bit more also careful about how the communication is happening. So the message passing, so here we are saying that messages are being sent between nodes, and this is called the message passing model. And it's synchronous and reliable. That is, when two neighboring nodes communicate, there's a global kind of a clock. So so if A is sending a message to its neighbors, at the same time, any other neighbor can send the message, and the messages are received at the end of the same time clock, right? So that's the standard synchronous reliable message passing model. Reliable here means there's no loss. So when you send a message, Now you can think of this in the terms of the last talk as kind of reachability. So it's when you say I'm going from here to here. So it's basically for us, for in this model, it's like sending a message. So this person is sending a message to this person. So this reachability. So if you can send a chain of messages to somebody else, you can reach them, right? That's the idea. So if there's a global clock, then it's synchronous. But if there's not a global clock, that is, you don't really have any bounds on when a message sent from here can reach here. So the time goes sort of out of the question, out of sync, it becomes asynchronous. And for a particular result later on, I sort of define something called an adaptive round asynchronous, which is you still have global rounds, but the delay is in terms of the global clock tick. So instead of fractional delays, we say, okay, you send from here to here, it takes you 3 clock ticks or 4 clock ticks instead of 3.25, which we do not know about. So that's sort of the idea. And we can also bring in anniversary. Okay, so that's sort of the technical kind of thing on this, but the problem itself is very simple and very interesting, hopefully, to understand. All right, so here's sort of the game. So the game here is the, sort of a broadcast, a word of mouth announcement. So if there's a professor and wants to announce that I'm going to have a class in a pub, now that the pubs are open, I can just tell one student and the news spreads like wildfire. If it was supposed to be a classroom, I suppose nobody would have bothered, but it's a pub, so the message will go forward. Or the more even favorite kind is political news. So if somebody says, I hate this politician, and then just send to somebody, one of its neighbors or all of its neighbors, just everybody sends to everybody else. So now this kind of algorithm itself is called flooding. It's very dumb, but it's the most fundamental of distributed algorithms. So the algorithm of flooding is simply where if you have a message, you just send it to your neighbors, and then they just send to all of their neighbors. So everybody just sends to everybody. So that's basically flooding. But here we have a slight twist, and then we call it amnesiac flooding for this reason. What's the slight twist? The twist comes from the original motivation of the WhatsApper. So the WhatsApper is ambitious. That is, it does flooding. If it has a message, it will forward. It will not wait. It's also amnesiac. So amnesiac, the word amnesia basically means a short-term memory, right? So if you've seen pictures like Memento, you know what I mean. So you forget very quickly. So amnesiac means I shall not remember the past, which means I just remember here the immediate round. So if I receive the message, right now, I will send it and then I will forget that I ever saw that message. So that means if it comes again, I'll still send it. That's how this differs from classical implementation of flooding, which is a very, very old algorithm where you could keep a flag and say, I've seen this message before. Also, it's polite. So polite here again, I mean, if you've just sent me the message, I will not send it back to you right away, right? So nodes are only remembering the previous round, so they don't have any explicit message flags, and they're sending message to exactly all those who did not receive in the previous round, right? So that's sort of the setup. So more formally, amnesiac flooding begins in this manner. Now this is single source flooding. We do have the solutions for the multi-source flooding also, but it's not part of this presentation. So single source flooding here is you have a distinguished node L. So this node has this piece of information it wants to send to everybody. And the first round it sends to all of its neighbors. And in subsequent rounds, everybody who's receiving the messages from a subset of their neighbors or from all of their neighbors will send back to the complement of that set, right? So they will send to all the neighbors except themselves. Now, this is a very simple flooding process, but interestingly, it was never sort of, the question was, I don't know if it was possibly postulated, but never seriously thought about that, if you just use this process, will this ever terminate? So termination here means that, is it possible that this messages stop flooding the network, right? It's a very important question in some sense, because it basically means if it doesn't terminate, then you keep sending the message around forever. And remember, you don't have a flag. So in classic distributed or in classic flooding, which is basically the fundamental algorithm, whenever you set up a network, you don't know anything, the first thing you will probably try to do is just flood. And other protocols like gossip and things have taken over, where you don't send to everybody, but flooding is basically the main alternative. So but what you did there was you kept a flag that said, I've seen this message, so if it comes again, I will not send it forward. Now that was explicit termination, but that has an overhead, which means you need to remember all of the messages you've seen in the past history. And that means you're using much more local memory. So if you want to avoid that, now if this thing works, it doesn't use any memory. So that's fantastic, because you don't need to remember anything, except if you follow this precise process. And that's where, of course, slight catches. Okay, so first question is, will it terminate? And second question is, how long does it take to terminate? So like I said, termination means there comes a stage where nobody's sending the message anymore. So how can that happen? If intuitively, if you already start thinking, the only way that can happen is either a node doesn't have the message, or it's been sent the message by all of its neighbor at that time, and then it cannot send to anybody. So those are the two ways, right? And second, very interesting question: how long does this take? Does it stop? Is it good? Is it efficient? Okay, let's look at some examples, some simple examples. Okay, so first let's look at a line graph. So we have a line graph. So let's say this node B is originating the process. In round 1, B is sending to both its neighbors A and C. Now in round 2, both A and C have the message. Now C cannot send back to B, A cannot send back to B, so A is done, cannot send forward. C can send to D, so it sends to D, and now D cannot send to anybody else, so this actually stops. So it's actually stopping in 3 rounds here. And one can sort of imagine any line you get, this process should stop, right? But now let's look at a triangle or a clique or an odd cycle, right? So triangle is an example of both a clique and an odd cycle. B again starts the process. Round 1 sends to A and C. Now A and C can send to each other, right? Because they haven't sent to each other before. So A and C send to each other. Now A and C has got the message again, a second time. So this is sort of the danger, right? So, but they cannot send back to each other because they just got from them, but they can send back to B. It started the process. Now B is receiving from both of its neighbors, A and C, so it's actually cannot send it forward anymore. So B stops. So the triangle also, it stops. Interestingly, if you notice in the triangle, somehow A and C sort of receive the message twice, whereas in the line, none of the nodes receive the message again, right? So there may be something which is happening here, right? Okay, what about an even cycle? So an even cycle is like a square, for example. So B sends to A and C. Now A and C got the message, they send to D. Now D got the message simultaneously. Of course, it cannot go further. So it stops. Now somehow, if you notice, this seems to have stopped a little bit quicker. It just took 3 rounds, even though there were 4 nodes, whereas a triangle had 3 nodes, but it took it 4 rounds, right? So something dicey happening here. So both of them terminate, right? Now you could have, of course, much more complex topologies. So for example, you could have this funny kind of one-eared rabbit or something, I don't know. So B sends to C and A, and then C sends to E and F, and E and F crossover. It's a triangle fixed onto a square, and then it comes back, and then so on, around 5. Now around 6, they come back into the square, and then again, they happen to terminate at A. Not at B where it started, but terminated at A, right? So again, this process terminates. So far, empirically, the evidence we're getting is it seems to terminate. And that's sort of the state we were for about a year or more, till my colleague at Loughborough University actually came up with a nice proof. But okay, let's look at some very famous, well-known topologies. So you could have hypercube, you could have Peterson graph, right? These kind of things. So it's just a simple question. You have a graph, and now you could probably define in terms of, I don't know, other processes, feasibility kind of things, but this is the process which is happening. Will the process stop? Will the process terminate? Now let's look at the hypercube, and I have these illustrations here. So you can see if you begin from this node 1, from this node in red. In the hypercube, it seems to go all the neighbors and all the neighbors, and then it's terminating in 3 rounds. So, I've already taken so much time. Okay, sorry. All right, so hypercube is terminating in 3 rounds. In Peterson graph, it's taking in 5 rounds, where diameter is just 2. So something crazy is happening here. Okay, so since I took way more than I planned on the introduction, so I have to do it quickly. Okay, so the basic thing is AF termination. Does AF terminate? Actually, yes, it does terminate. Does it terminate on every graph? In fact, it does, which is quite surprising. So it terminates on every graph. And here's sort of a quick proof. I'll have to skip the proofs now since I'm out of time. But sort of the idea is the cute idea of the proof for saying termination is simply the following. If you look at the rounds where everybody is receiving message, and we define it as a round set. What is the condition for non-termination? That's the nice thing. So condition for non-termination is that there must be at least one E where you have the same node repeated, right? And okay, so if we come back to this this slide, it sort of says that, you know, if you consider the first 3 such rounds, there must surely be 2 which are evenly spaced. That's sort of the idea. So the idea is, if you can show that there are no even rounds in which there is a repetition of the same node, then you're done, because there must be evenly spaced rounds in which the same node repeats for a non-terminating process. So with sort of that, we can set up a contradiction and show that no, actually, with a couple of contradiction proofs, we can actually find that there's no that this process actually terminates. So which is a nice thing. So this process actually terminates on every graph. So again, as I said, I'll skip through the proofs. Is it quick? Now that's sort of another very interesting question. Is it quick? Actually, we discovered, yes, in fact, it is quick. And the termination times, okay, so like we said, it seems to be in some cases terminates visits only once, in some cases visits twice. Now, why this difference? So that difference actually comes in this manner. If you notice, the graphs which have these properties of visiting only once are actually bipartite graphs. And the graphs which have the property of visiting more than once are non-bipartite graphs. So it turns out that there's a class differentiation here. So in bipartite graphs, it finishes in less than D time. In non-bipartite graph, 2D plus 1 steps. So that's sort of the nice thing. And the proofs are a little bit more involved here. For bipartite graph, actually, it turns out the proof is very simple to see once you have the idea. And the proof is simply that you can start a BFS breadth first search traversal from the origin node. And if you keep going down, there are no cross edges in the BFS tree, right, of a graph, of a bipartite graph. So messages can only go down. And if they can only go down, they have to terminate in the diameter time, right? They have to just finish later on. So actually in eccentricity time, if we are now more formal, the time for termination in bipartite is eccentricity time from the origin. Okay, I'll just skip here. And for the non-bipartite graph, it's more involved. It's actually, there's a range of termination times starting from at least eccentricity, but goes up to E plus D plus 1. So that is up to 2D plus 1, right? So again, I'll skip the proofs here, but those are sort of the main results which come out here. And now, interestingly, if you have asynchronous, the thing is, if you are allowed different time delays and there's, say, an adversary which can decide, it can actually make the process non-terminating. So how's that? For example, in this message, in this example, B sends to A and C are sending to each other. Now, when C sends to send back to B, it delays by time 2. So it takes 2 time steps. And now when B receives the message, it still has not received from C, so it doesn't know that. So it sends to C, and now the messages cross over, and it can keep repeating this. So there are ways in which, if this process is played with, it can become non-terminating, right? So that's sort of the interesting thing here. Now, in recent follow-up work, the sort of the obvious question is there what about multiple sources? So we have gone beyond this, and we've discovered even if you start from any number of sources, the process still terminates. Only the interesting thing is it'll take different termination times. And that is something we're still studying in detail. For example, if the process starts from every node, then it's sort of easy to see it's going to terminate in one time step. And if it's on a, say, a click, it takes about 3 time steps. So there's sort of different notions here. Also, there's been follow-up work by, say, Volker Turau, if I pronounce correctly, where used an alternative method like an auxiliary graph, which reduces non-bipartite to bipartite graphs. And there's another variant introduced by him called K-amnesiac flooding, which is saying, what if you have K starters? What is the best placement for these starters so that they have the smallest termination time, right? Things like that. Now, making a connection to temporal graph theory with distributed theory, there's an interesting paper from Stock 2010, which is by these authors, Kuhn, Lynch, and Oshman. And they have a model called distributed dynamic graph model, which I believe has a lot of similarities with the temporal graph model. And the idea is they have a fixed set of nodes with changing edges and with communication proceeding in synchronous rounds. They do have this thing called T-interval connectivity, which is that for every block of T consecutive rounds, there is a connected spanning graph, subgraph, which remains stable. And they interestingly can show many things can be done in that. For example, if you have one interval connectivity, the graph stays connected every round, but can change completely every round. So the graph completely changes every round. I'm sure you can put temporal constraints on the edges and achieve the same kind of idea. Or if you have an infinite interval connectivity, which means there's a permanent unchanging subgraph, but other edges can completely change all the time. And surprisingly, this show you can count network size and do other functions and things like that. So the question would be, how would AF or some of its variation seem in temporal graph or dynamic graph model? There's something still to explore. For example, if you have this square below and you have, say, the origin node is on the top left, and the neighbors are having odd times and the other edges are having even times. So I think this one would follow just the regular results, because you should be able to send the message around on odd and even times. But if the starting node is different, then it may cause different things. So, but there's a lot of things to think what it means to be arriving simultaneously. For example, what does that mean in this context? All right, so to conclude, amnesiac flooding is a very lightweight communication method that achieves broadcast in almost, I can't really see behind here, but optimal time. So, and termination times differ sharply in bipartite and non-bipartite graphs as a function of diameter. Now, this can suggest you could possibly use this to test topologies. So if you had an idea of eccentricity times or diameter, you could possibly try to find out if your graph is bipartite or non-bipartite. It may succeed in some cases, but it's not completely clear if you may get an approximation kind of thing only. So, and in asynchronous networks, in certain cases and adaptive adversary, you can force non-termination. So there are many open directions. There's more asynchronous settings of the graph parameters, randomized delays and links, etc. So thank you. Sorry, I had to skip most of the technical details, but hopefully I can answer them offline. So thanks again.
That's great. Thank you very much, Amitabh.